Hello, everyone. My name is Engela Sthapit. I'm a NOAA EPP MSI CSERT graduate fellow at the Department of Civil Engineering at the City College of New York. Today, I'm going to talk about my research work on evaluating snow and streamflow in NOAA MP and World Hydro Model, which is a case study in the Aroostook River Basin in Maine. And the background in the slide is from that area. My faculty advisors and mentors are Drs. Kandenberdy and Dr. Lockinger, and my NOAA mentors from NOAA ESRL PSL office in Boulder are Rob Spelly, Dr. Rob Spelly, Mimi Hughes, and Kelly. So I would like to start with a brief introduction on snow, like why we need to study snow. That's because the snowpack influences energy balances and surface heat fluxes, and it's really important for surface albedo, which is like a big part of the heat balance. It also is important because of the snow melt, especially during spring, which is important for water resources management, like water availability in terms of municipal water use or recreational purposes, and also has important role to play in flooding and drought. The picture in the background is our NOAA CSERT and joint NOAA CSERT and CUNY experimental site. We call it CUNY Safe up in Caribou, Maine, where we have radiometers and med station and sensors to measure snow water equivalent. One other important aspect of why we need to study snow is because many local socio economies depend on snow for agriculture, for recreational purposes, and also for migratory animal herds. How I was exposed to the socioeconomic side of things were when I was in Caribou, Maine. This was before the pandemic. We were involved in roundtable discussions with the local economic council and their local Native American Micmac community, where we were discussing how the snow impacts their economy and how it's important for them. And we were also involved in community outreach and K-12 STEM education programs. We're demonstrating, balloon launches and talking to the high school students about meteorology and how to measure snow and all that stuff. So it was a great experience. So getting back to my research, so the start point is to understand like how snow is changing due to the rise in the temperatures in the past few decades. Many studies have shown that snowpack is decreasing during winter, so the water availability is actually increasing during the winter because of all this snow is melting early. So that there is a shift in the timing of streamflow because of the decrease in snow water equivalent and snow depth during the winter, but which is increasing the availability of water during the winter, but decrease during the spring. And these changes are expected to be substantial or more substantial for smaller headwater basins compared to the larger basins. And that's my picture up on the snow mound. So there are different ways to models or study snow, know more about snow. Like one of them is you can use statistical models, you can use numerical water prediction models, or there are like remote sensing data products that allows you to monitor snow. The one that I'm looking at, especially for this research, is the numerical water prediction model, which is the part of National Water Model. It is the National Water Model is the state-of-the-art numerical hydrological prediction model that forecasts streamflow over the CONUS at 3,600 NWS location and many other 2.7 million actually locations, streamflow locations without any forecast. The core of the national water model is the NOAA NP land surface model that calculates the energy and mass balance in a vertical column, and a work hydro model that does the river routing. Oh, actually, the thing playing, which I wasn't going to do for the sake of time, so I'm just going to move forward. The numerical water prediction model, they do face challenges, mainly due to the uncertainty in the meteorological forcing data, which is like mainly radiation forcing, temperature, precipitation, relative humidity, pressure, and so on. Other difficulty is finding the appropriate parameterizations to model the processes, especially in the catchment scales that one is looking at. And the satellite remote sensing, like I mentioned before, it is a good supplemental data in numerical prediction, because it provides like continuous coverage in time and space where we don't have the observations like in the remote areas. Although it does have its own challenges, because sometimes the retrieval algorithm is difficult and the resolution is so small, but it does have a very important role to play in snow observation. So my research questions were, I was trying to look at what insights can I get from comparing the model simulation with different forcing data sets. And the ones that I was looking at was the forcing data from the safe experimental station. We had the observation of the meteorological forcing. One of them was that, and the second one is the NLDAS2 data sets, which is the National Land Assimilation Data Set version 2. And this is the single column experiment, which is like this one grid. And the second part was to do a Basin Study, where I was gonna look at the work hydro model's performance in retrospective National Water Model 2.0 of version simulation, to look at how well does it predict stream flow, and also if remote sensing can help to fill some of the deficiencies that we find there. So this is the study site that I mentioned before. It's in the northeast, eastern Maine. The outline in black is the Aroostook River Basin, and within that there are 4 sub-basins that I did the basin study on. That's the circles, and then the CUNY safe site in Caribou is the one in dark. And within the basin, I wanted to point out that in the two smaller basins, the land use was dominated more by agricultural lands, whereas in the bigger basins, it was more forested, because that seems to have played a role in the stream population, which I'm going to show later on. So data set, like I mentioned before, met data from NLDAS2 and QVSafe, Streamflow data, observational data from USGS for comparison purposes, and remote sensing data from MODIS. There is a product snow cover data called mod 10 A1F. So the first results shown here are differences between the model simulation of snow water equivalent and snow depth. 2 model simulation, one that was forced with the station observation and the second that was forced with the NLDAS2. The one in the blue lines are the NLDAS2 results, and the yellow one or the orange one are the station results. And we can see that for all the years that I looked at from 2014 to 19 water years, the NLDAS2 was higher than the station force model. The SWE and snow depth were higher for all the years. So what is causing these differences? So we go look at the forcing data, what was the differences between the forcing data that's causing or like contributing to these differences. The first one is the incoming long wave radiation. There was a negative bias in the NLDAS2 had a negative bias in the incoming long wave radiation compared to the station. For incoming short wave radiation, there was a high positive bias. The temperature T2M is the 2 meter air temperature. It had a negative bias, and relative humidity had a positive bias. So these are the major ones. So these are the results from the Streamflow. The two figures to the left are the smaller basins, Hardwood Brook and Little Madawaska, and the two figures to the right is Masardis and Washburn. They are the larger basins. So you can see that the two smaller basins to the right, my right, the Streamflow was not quite as well represented. The yellow or the orange is the observation MPUS gauges, and the blue is the model simulation. So at Hardwood Brook, it was over predicting, and at Madawaska, it was under predicting. But for the bigger basins such as Masardis and Washburn, the model was doing pretty well. I didn't show the statistical numbers, but just a snapshot, and I had it if you want to see it. So the last results are, I was trying to look at how does the model simulation of stream and snow depth, snow water equivalent snow depth and fractional snow cover area in the model, how well, how does it help with the, how does it correlate with the stream flow in the model. So this is just for one watershed that I'm trying to show it. I know it's a very busy graph, but the green and the magenta lines, those are the SWE and snow depth. And down there is down there at the the blue and the red are the stream flow. So you can see that's a very good correlation or very good match between when the SWE and snow depth goes down, the stream flow starts to go up. As for the fractional snow cover area in the model, which is the olive green line, it was pretty binary, so it wasn't very helpful. There was not a lot of variation. It wasn't very helpful in like it was an indicator of snow melt during the spring. But this is where the remote sensing data comes in. The MODIS fractional snow cover data had a potential to cover where the model's fractional snow cover area wasn't giving us a lot of information. So to wrap this up, the higher SWE and snow depth from the NLDAS2 force model, it was mainly due to the biases in the 2 meter air temperature in NLDAS2. This was because of the partitioning scheme that was parameterized in the model, which was based on the 2 meter air temperature. That was the result of that. And other things that were influencing were the positive bias in surface radiation, the surface radiative temperature, and also the parameterization of fractional snow cover area, which I didn't go into too much detail. For the basin study, like I mentioned before, the smaller basins were not doing as good as the larger basins, and like I mentioned before, it might be because one of the factors might be because of the land use. The smaller basin had a lot of agriculture area, whereas the larger basins were more forested. The simulated snow depth and SWE was is very valuable. Seems it's very valuable to time the snow melt during spring, which impacts the community a great deal because of the flooding and other things that are associated with it. And remotely sensed MODIS data was provided some good insights. So I'd like to thank the NOAA EPP for the and CSERT for the grant support for this work, and especially I'd like to thank my NOAA mentors who were instrumental in this research, without whom I would not be able to do the work that I. Thank you.
Got time for at least one question. Let's give her one question. All right.
So with the influx of fresh water due to the snow melt, at what magnitude is the smaller basin's water level rising in comparison to the bigger basin?
I didn't look at the stages. I just looked at the flow.
All right, let's thank all of our speakers.